In this video, we will see some properties of integrals which are similar to the properties we saw for limits. This is because integral is in some sense a limit, though not exactly as we have seen before. So let us see these theorems one after the other. Let's see the first theorem. So let f and g be in RAB, that means they are both Riemann integrable, then A, if K belongs to R, then KF belongs to RAB, and integral from A to B KF is equal to K times integral of A to B of F. Let's immediately see the proof of this statement. So notice that if P dot is a partition xi minus 1 comma xi comma ti, so P dot is a tagged partition, then S of KF P dot is equal to K times S of F P dot. Why is this the case? What is S of KF P dot? It's nothing but summation of KF at Ti into xi minus xi minus 1, which is equal to K into F of Ti into xi minus xi minus 1, summation of this as I going from 1 to n, and the K will then come out, so you get K into summation I going from 1 to n F of Ti into xi minus xi minus 1. So we get that these two are equal. Okay, so this tells us that SKF P dot is equal to K times S of F P dot. As F is integrable, we know that for every epsilon greater than 0, there exists a delta of epsilon such that norm of P dot less than delta of epsilon implies that mod of S of F P dot minus integral of A to B F is less than epsilon divided by K. Okay, we can find such a delta of epsilon. But this implies that mod of S of KF P dot minus K times integral of A to B F is equal to modulus of K times S of F P dot minus K times integral A to B of F. Why is this equality true? Because we showed that this is equal to this earlier. So because of that, we see that the two sides of this equation are equal. Now we can take K common and take it outside the modulus and write it as K into modulus of S of F P dot minus integral A to B F. But we know that if norm of P dot is less than delta of epsilon, then this quantity is less than epsilon by K, which implies that we have this is less than or equal to K into epsilon by K, which is equal to epsilon. And that completes the proof. Similarly, assuming f and g are Riemann integrable, f plus g also is Riemann integrable. Moreover, integral A to B of f plus g is equal to integral A to B of f plus integral A to B of g. Okay, and the proof idea is quite similar to the previous case. The most important bit is S of f plus g P dot is equal to S of F P dot plus S of G P dot. And the proof of this is very similar to what we saw earlier, so I leave this as a homework. Okay. Now let's assume this and then complete the proof of the result. So f is Riemann integrable implies that for every epsilon greater than 0, there exists a delta 1 of epsilon such that norm of p dot is less than delta 1 of epsilon implies that mod of s of f p dot minus integral a to b of f is less than epsilon by 2. Similarly, G belongs to R of AB implies that for every epsilon greater than 0, there exists a delta 2 of epsilon such that norm of P dot is less than delta 2 of epsilon implies that mod of S of GP dot minus integral A to B of G is less than epsilon by 2. So if delta is equal to minimum of delta 1 of epsilon and delta 2 of epsilon, then norm of P dot is less than epsilon, delta epsilon implies that modulus of S of F plus G P dot minus integral A to B of F plus integral A to B of G is equal to modulus of S of F P dot plus S of G P dot minus integral A to B F minus integral A to B G, which by triangle inequality is less than or equal to modulus of S F P dot minus integral A to B F plus modulus of S G P dot minus integral A to B of G, which is less than or equal to epsilon by 2 plus epsilon by 2, which is equal to epsilon. And that completes our proof of the result. Finally, we prove that if f of x is less than or equal to g of x for all x in AB, then integral a to b f is less than or equal to integral a to b g. So again, for every epsilon greater than 0, there existed delta of epsilon greater than 0 such that S of f p dot minus integral a to b f is less than epsilon by 2 if norm of p dot is less than delta of epsilon. And similarly, S of g p dot is minus integral a to b g is less than epsilon by 2. Again, if norm of p dot is less than delta of epsilon. So we can rewrite this as minus epsilon by 2 less than S of f p dot minus integral a to b f. So I take this to this side, so it will become integral a to b of f minus epsilon by 2, which is less than integral a to b f plus epsilon by 2. Similarly, I get integral a to b g minus epsilon by 2 is less than or equal to S of g p dot is less than or equal to integral a to b g plus epsilon by 2. Finally, we can prove that irrespective of which partition we take, S of f p dot is less than or equal to S of g p dot. Okay, this is similar to what we did for skf p is equal to s of fp, k times s of fp dot, and I just leave this as a homework. Okay, so I assume you prove that, and then you look at this inequality, and this inequality together. So what happens? We know that integral a to b f minus epsilon by 2 is less than or equal to s of fp dot, which is less than or equal to s of gp dot, which is less than or equal to integral a to b g plus epsilon by 2. So this implies that integral a to b f is less than or equal to integral a to b g plus epsilon. But as epsilon is arbitrary, we have the proof.